January 28, 1944. The village of Slotopol in Ukraine, west of the Dnieper. The temperature is 15 degrees below 0 Fahrenheit. A column of Panther tanks belonging to Panzer Regiment 23 has been ordered to march 75 kilometers across frozen roads to reinforce a German salient that is, although the men in the tanks do not yet fully understand it, in the process of becoming the Korsun-Cherkasy pocket. 60,000 German soldiers are about to be encircled by the Red Army. The Panthers, the most advanced medium tanks in the German inventory, are being thrown into the gap as the last available armored reserve. They never arrive in fighting condition. Of the tanks that begin the march from their railhead, several are lost before they reach the assembly area. One Panther catches fire in the engine compartment and is completely destroyed by its own crew before the column has moved 15 kilometers. A Burge Panther recovery vehicle sent to drag it out of the way also catches fire and is permanently disabled. 5 additional Panthers limp into the assembly area with various mechanical problems. One has a final drive leak. One has an idler wheel bearing that has come apart. One has a damaged radiator. One has a fuel pump failure. One has driven off a bridge and cannot be recovered. The battalion reaches Slotopol with fewer tanks than it left with, and the fighting has not started yet. Across the entire Eastern Front, in the late winter and spring of 1944, this scene was being repeated over and over. German panzer divisions were marching to combat zones and losing tanks before they got there. Panthers were breaking down on roads. Panthers were being abandoned in fields. Panthers were being blown up by their own crews because there was no time to repair them and no possibility of recovering them, and because abandoning a tank to the advancing Red Army was unacceptable. The reasons varied. Sometimes a fuel pump failed and started an engine fire. Sometimes a head gasket blew and dumped coolant into the cylinders. Sometimes the transmission seized. Sometimes the tracks broke. But running through all of these mechanical losses more consistently than any other single cause was one specific failure. A single component, a pair of straight-cut steel gears about 18 inches in diameter, located inside the housing where the drive shaft from the transmission turned the sprocket that drove the tracks. The component was called the final drive, and the failure of that component, more than any single armored confrontation, more than any tactical defeat, more than any error of generalship, was the mechanical pathology that quietly destroyed the offensive capacity of the German Eastern Front from the summer of 1943 until the end of the war. Most of what is written about the Panther tank, in the popular histories and in the documentaries and in the modeling magazines and in the YouTube videos, focuses on what the Panther did well. It was an excellent design in many ways. Its long, high-velocity 75mm gun could penetrate a Soviet T-34 at 2,000 meters. Its sloped frontal armor was nearly invulnerable to most Allied anti-tank weapons. Its optics were superior to anything the Red Army fielded. Its crew layout was sensible. Its commanders, when they had operational Panthers, considered them the best medium tank of the war. General Hasso von Manteuffel, who commanded Panther units in combat, said that the Panther would have been close to the ideal had it been possible to design it with a lower silhouette. These judgments are accurate, as far as they go. The Panther was, in a tactical engagement, a deadly weapon. But a tank that cannot reach the battlefield is not a weapon. A tank that breaks down on the road march is a piece of expensive steel scrap. A tank whose crew has to abandon it in a retreat because no recovery vehicle can drag it out of the path of the advancing enemy is, in the most precise military sense, a gift to that enemy. And throughout 1943 and 1944, the operational readiness rate of Panther units on the Eastern Front never exceeded 35%. Sometimes it dropped to 16%. By contrast, the Soviet T-34 units that they were fighting against routinely operated at 80 to 90% readiness. The Panther's combat record, in the individual engagements where it managed to fight, was excellent. The Panther's strategic contribution, measured by how often it actually reached the battle, was catastrophic. The reason for that gap, That difference between tactical excellence and strategic disappointment lay inside a small steel housing on each side of the tank, just behind the front road wheels. To understand how the most modern tank in the German inventory became a permanent maintenance crisis, you have to understand what a final drive is, why the Panthers was designed the way it was, and what happened to it when the tank that had been designed to weigh 35 tons grew during development to weigh 45.
In any tracked vehicle, the engine produces power at high speed and low torque. The tracks which actually move the vehicle require low speed and high torque. The reduction from the engine's output speed to the track's working speed is accomplished in several stages. The transmission gearbox makes the first and largest reduction, dividing the engine's RPM by perhaps 10 or 12 to 1 in the lower gears. The final drive, located between the transmission and the drive sprocket on each side of the tank, makes a further reduction, typically by another factor of 3 or 4 to 1. It is the last stage of the gear train, the place where the torque coming out of the transmission gets multiplied one final time before it reaches the sprocket and pulls the track around the road wheels. In a heavy tank, the loads at the final drive are extreme. Every time the driver accelerates, decelerates, turns, or climbs a grade, the entire torque demand of moving 40-plus tons of armored vehicle passes through those last gears. The gears must be hard enough to resist surface wear, tough enough to absorb shock loading, accurate enough to mesh smoothly under millions of cycles, and large enough in cross-section to carry the loads without fracturing. The Panther's final drive was none of these things. Not really. Not enough.
The story of how it became inadequate begins with a man named Karl Otto Sauer. Sauer was not an engineer. He was an administrator. He had risen through the Nazi Party bureaucracy in the 1930s, and by 1941 he was the chief director of armament and war production, reporting directly to Albert Speer, the Reich Minister of Armaments. Sauer's job was to extract production, to make more tanks, more aircraft, more guns, more ammunition, to do this faster, to do this with less skilled labor, fewer machine tools, less material. Sauer was by reputation a brutal manager who pushed every program he was responsible for to the limit of what its engineers said was possible, and then beyond. He clashed repeatedly with the technical staff at MAN, the Maschinenfabrik Augsburg-Nuremberg, the firm that had won the design competition for what became the Panther. He clashed with Henschel, which built the Tiger. He clashed with Krupp. He clashed with Daimler-Benz. His instrument when he clashed with these firms was simplification. If a part required too many machining operations, Sauer wanted it simplified. If a part required scarce materials, Sauer wanted those materials substituted. If a part required time-consuming heat treatment, Sauer wanted the heat treatment shortened or eliminated. When the Panther entered detailed design in 1942, its original specification called for a planetary gear final drive of the type used in the Tiger heavy tank. A planetary gear set is mechanically elegant. It distributes load across multiple gear teeth that engage simultaneously, sharing the torque among 3 or 4 planet gears that orbit around a central sun gear inside a ring gear. The load on any individual tooth is a fraction of the total. The whole assembly is compact, runs in a small space, and can be sealed and lubricated in a closed housing. The Tiger used a planetary final drive, and the Tiger's final drives, despite the legends that have grown up around the heavy German cats, were reasonably reliable. The intention in the spring of 1942 was that the Panther would inherit this same design, with appropriate modifications for the lighter tank. That changed during 1942. The reason, depending on which post-war source you trust, was either a shortage of the specialized machine tools required to cut planetary gears at the rates Sauer demanded, or Sauer's own intervention to simplify the design, or some combination of both.
The technical literature is contradictory on the question of whether Sauer personally ordered the change or whether Mann's engineers volunteered it under production pressure. What is clear is that the final drive was changed before the first Panther reached the field from a planetary system to what the Germans called a Stirnradgetriebe, a two-stage spur gear system. Two straight-cut spur gears, one for each stage of reduction, arranged in tandem inside a steel housing. The spur gears could be cut on conventional gear-cutting machinery that German shops already possessed in quantity. They required less specialized tooling, they could be heat-treated in standard furnaces, they could be assembled by less skilled labor. They were, from a mechanical engineering standpoint, much simpler to make in the quantities the Wehrmacht demanded. They were also, from a mechanical engineering standpoint, much worse.
A straight-cut spur gear engages one tooth at a time, or sometimes two, depending on the gear's geometry and what engineers call the contact ratio. Each tooth, as it comes into mesh, takes the full load until the next tooth picks up the load. The impact of engagement, the sudden transfer of force from one tooth to the next, sends shock through the gear material. A helical gear, by contrast, engages its teeth gradually, with the load spread across multiple teeth simultaneously and the contact lines sweeping smoothly along each tooth as it rotates. A double helical gear, sometimes called a herringbone gear, splits the load further by using two sets of helices arranged in opposite directions, canceling out the axial thrust that single helical gears generate and distributing the load even more smoothly. The American Sherman tank, which fought the Panther across France and Germany in 1944 and 1945, used double helical final drive gears. The British Cromwell used helical gears. The Soviet T-34 used herringbone gears in its final drive. The Panther used straight-cut spur gears. That single design decision, the substitution of straight-cut spur gears for the original planetary system, was the seed of every operational catastrophe that would follow. By itself, it would have been a problem. Combined with two other factors, weight growth and steel quality, it became a disaster. The Panther had been designed in 1941 and 1942 to weigh approximately 35 tons. As it moved through development, the design grew. The armor was thickened twice. The turret was redesigned to mount a longer, more powerful 75mm gun than originally planned. The engine was upgraded from the Maybach HL210 of 650 horsepower to the HL230 of 700 horsepower to handle the additional weight. By the time the Panther entered series production at MAN in January of 1943, it weighed 45 tons. The final drive, however, had not been redesigned. It was still the two-stage spur gear unit specified for the lighter tank. The gears, which had been adequate, if not exemplary, for a 35-ton vehicle, were now being asked to transmit the torque required to move a 45-ton vehicle. The engineering calculations, performed by various post-war analysts and verified by mechanical engineers who have examined surviving Panthers, show that the stress on the most heavily loaded gears in the Panther's final drive was nearly 4 times higher than the stress on the equivalent gears in the Tiger I. The Tiger weighed 57 tons, more than the Panther, but its final drive used planetary reduction that distributed the loads across multiple teeth. The Panther's two-stage spur gears, despite being in a lighter tank, were carrying loads that no straight-cut gear of that size and material could be expected to survive for long.
The material was the third factor, and the one that turned a marginal design into a doomed one. The steel from which the Panther's final drive gears were forged was, by the standards of 1943 and 1944 German metallurgy, the best available. But the best available was no longer very good. Germany had been at war for 4 years. The high-quality alloy steels of the pre-war period required substantial inputs of nickel, molybdenum, and tungsten. The nickel came from Petsamo in Finland, the molybdenum from a few small mines in Central Europe, the tungsten almost entirely from Portugal and Spain through complex sanctions evasion supply chains. By 1943, all of these strategic alloys were in short supply.
German metallurgists were forced to substitute. Lower alloy steels were used where higher alloy steels would have been preferred. The case hardening process, which produces a hard outer skin on a gear tooth with a tough core underneath, was the only practical way to compensate for the inferior base material. But case hardening at the scale Germany was producing tanks required time, fuel, and skilled labor, all of which were in short supply. A report by an engineer named Puschel from MAN, written during the war and uncovered in post-war German technical archives, identified the failure mode with chilling precision. The intermediate gear in the Panther's two-stage final drive was failing in fatigue, Puschel wrote, due to the low core strength of the material and the absence of adequate case hardening. The gear teeth were not snapping off because of a single overload event. They were cracking and propagating cracks through repeated cyclical stress, exactly the failure mode that case hardening of a tough alloy steel is designed to prevent. When the case hardening was inadequate or absent, the underlying soft steel could not sustain the cyclical loads. The teeth cracked. Sometimes one tooth would crack and the others would carry the load for a while. Sometimes a tooth would snap off completely. When that happened, the broken piece would jam between the other gears and the entire assembly would shatter inside its housing. The tank would coast to a stop, smoke pouring from the sprocket housing, the driver feeling the steering wheel suddenly go dead in his hands as the track on one side stopped turning. The first Panthers reached frontline units in May of 1943. They were assigned to two newly formed Panzer regiments, the 51st and 52nd, and trained for the coming summer offensive against the Kursk salient. The training period was rushed. Crews had perhaps 4 to 6 weeks of familiarization on tanks that were arriving from the MAN, Daimler-Benz, M&H, and Henschel production lines as fast as the factories could ship them. Mechanical problems began appearing immediately. Fuel pump leaks ignited engine fires. The first model Panthers, the Ausf-D, had a fuel pump arrangement that placed 2 pumps near the exhaust manifolds. The pumps leaked. The fuel ignited. 3 Panthers were destroyed by fuel pump-caused engine fires during Operation Citadel alone, the codename for the German offensive at Kursk that began on July 5, 1943. But the larger problem, the one that would dominate the rest of the Panther's service life, appeared during the road marches to the assembly areas. The 75-kilometer road march from the railheads to the jumping-off positions for Citadel was, for many Panther crews, the first sustained operation their tanks had performed. The tanks broke down in numbers that shocked their commanders. By the time the offensive opened on July 5th, of the approximately 200 Panthers that had been committed to the operation, only 184 were operational. By the end of the second day, the number was around 50. By July 10th, it was approximately 10. 25 Panthers had been completely destroyed, 65 were under repair, and 100 more were waiting for repair, of which 44 had been damaged purely by mechanical failure rather than enemy action. The Soviet generals at Kursk had been bracing for the Panther. Intelligence reports had warned them that a new heavy German tank would be introduced into the battle. They expected, based on those reports, to face hundreds of Panthers operating as a coordinated armored force. What they faced instead was a thin scattering of Panthers, mostly broken down or in transit, fighting in small groups whenever the surviving few could be assembled. The Soviet T-34s and Su-152 assault guns destroyed the Panthers that they could reach, but the Panthers that the Soviets did not destroy were mostly destroyed by their own crews, who burned them in place when they could not be repaired, or simply walked away from them when the German lines fell back.
The pattern set at Kursk repeated itself for the next 2 years. Wherever the Panther was sent, mechanical losses ran significantly higher than combat losses. A British technical intelligence team examined 96 Panthers captured or destroyed between August 8th and August 31st of 1944 in the closing phase of the Normandy campaign. Of those 96 tanks, 11 had been destroyed by armor-piercing shot from Allied tanks or anti-tank guns. 1 had been destroyed by a hollow charge weapon, 1 by artillery high-explosive shell, 2 by rocket projectiles from aircraft, 1 by aircraft cannon fire, 44 had been destroyed by their own crews, 30 had been simply abandoned, 6 had been destroyed by causes the British investigators could not determine.
In other words, of the 96 Panthers examined, only 16 had been destroyed by direct Allied action. The remaining 80 had been lost to a combination of mechanical breakdown and the inability to recover them.
The Eastern Front numbers were similar. During the Soviet offensive that broke the Panther-Wotan line in mid-1944, German panzer divisions retreating from the Ukrainian heartland to the Dnieper bridges lost vehicles in catastrophic proportions. The 1st Panzer Army, which fought through the Kamenets-Podolsky pocket in March and April of 1944, began the operation with 838 armored fighting vehicles between its 1st and 4th Panzer Armies. Of those, only 300 were operational, 290 were in short-term repair, and 248 were in long-term repair. As the operation continued and the pocket closed and reopened, the tanks in repair were almost all lost. They could not be moved. The recovery vehicles, themselves Panthers converted into Berge Panthers, were themselves subject to the same mechanical failures as the tanks they were meant to recover. A broken-down Panther in a retreat was, in practical terms, a lost Panther. The Red Army would find it the next day or the day after, abandoned beside the road with its hatches open, sometimes with the demolition charges that the crew had set having failed to detonate completely. Heinz Guderian, the Inspector General of Armored Forces, understood what was happening. Guderian was one of the architects of German armored warfare, the man whose interwar writings had shaped Blitzkrieg doctrine, and by 1943 he was Hitler's senior advisor on tank policy. In a report dated March 5, 1944, Guderian wrote that one Panther-equipped unit on the Eastern Front had reported that the early mechanical difficulties had been resolved. The service life of the tank's engine had reportedly risen to 700 to 1,000 kilometers, which was the equivalent of 435 to 620 miles. Final drive breakdowns had ended, the report claimed, and transmission and steering gear failures were now within acceptable range. Guderian, an experienced reader of his subordinates' reports, recognized this for what it was. The acceptable range still meant frequent failures. The end of final drive breakdowns meant that they were no longer the dominant failure mode, not that they had been eliminated. A tank engine designed for 2,000 kilometers of service that lasted 700 kilometers was still failing at 3 times the design rate. By June of 1944, a British Army report cited a German prisoner of war who had served with a Panther battalion. He stated that the engines in his unit had an average service life of 450 miles or 724 kilometers. The factories building the Maybach HL-230 had begun, in November of 1943, deliberately derating the engines to a maximum of 2,500 RPM rather than the design speed of 3,000 RPM, simply to extend their service life. The derating dropped the Panther's maximum speed from 34 miles per hour to 28 miles per hour and reduced peak power from 700 horsepower to approximately 580. Crews who had been told they were driving the most powerful medium tank in the world were now driving tanks that had been deliberately handicapped to keep their engines from destroying themselves under combat conditions. The final drive problem was never solved. In September and October of 1944, Mann and the Heereswaffenamt incorporated a series of modifications to the Panther's final drive intended to address what Thomas Jentz, the dean of Panther historians, described as chewed-up gear teeth, broken parts, damaged bearings, and insufficient lubrication. The improvements helped at the margin. The case hardening process was tightened where the steel supply allowed, different lubricants were specified, the retaining bolts that held the large drive gear flange were redesigned, but the fundamental problem, that straight-cut spur gears of inadequate dimension made from inadequate steel were carrying loads they had never been designed for, could not be fixed inside the geometric envelope of the existing tank. There was no room in the Panther's hull to fit larger final drives. The whole vehicle would have had to be redesigned, and Germany in late 1944 was in no position to redesign the Panther. So the failures continued.
throughout the long retreat from the Dnieper to the Vistula to the Oder, throughout the Ardennes counteroffensive of December 1944 and January 1945, throughout the final defense of Berlin in April 1945. Hartmut Knittel's post-war study of German tank production, Panzerfertigung im Zweiten Weltkrieg, documented that officials at the Nibelungenwerke, the Austrian plant that built Panzer IVs, were openly aware that the final drives they were producing did not meet engineering quality standards. They built them anyway because the alternative was to build no final drives at all, and the front needed tanks. The factories were short on certain resources, and the heat treatment process was being experimented with as those resources varied in availability. Every late-war German tank, the Panzer 38T, the Panzer III, the Panzer IV, the Panther, the Tiger, suffered from broken final drives and bad bearings. The Panther was the worst affected because its final drive was the most marginal design relative to its weight. Inside the larger picture of the Eastern Front, the consequences of this single failure mode are difficult to overstate. The German army had begun the war with a doctrine that depended on the rapid, sustained, deep operations of armored formations, blitzkrieg. The whole concept assumed that armored divisions could be moved hundreds of kilometers across the operational depth of the enemy, breaking through, exploiting, encircling before the enemy could react. This doctrine had worked in Poland in 1939, in France in 1940, in the opening months of the Soviet campaign in 1941. By 1943, it was breaking down, and one of the reasons it was breaking down was that the tanks that had been built to execute it could no longer execute the road marches the doctrine required. A panzer division that could not move from one part of the front to another without losing 20% of its tanks to mechanical breakdowns was not, in any meaningful operational sense, a panzer division. It was a static force. It could fight where it stood. It could not be redeployed. When the Red Army's offensive doctrine, perfected in 1943 and 1944, focused on selecting weak points in the German line and breaking through them before German armored reserves could intervene, the bottleneck was no longer the German command system or the German tactical skill. It was the simple, brutal arithmetic of how many of their tanks could complete a road march without breaking down. The German tank crews understood this. They were the ones who had to abandon the tanks. They were the ones who pulled the demolition charges, climbed out, and walked back to the next defensive position, knowing that they would be issued a replacement tank from the steadily shrinking pool of operational Panthers in their unit. Many of them grew bitterly cynical about the equipment they had been given. The Panther was, in their own assessment, a brilliant fighting machine that could not be relied on to reach a fight. They sometimes preferred the older Panzer IV, which was less powerful but more reliable. The Stug 3 assault gun, based on a Panzer III chassis with a fixed casement instead of a turret, became the most produced German armored vehicle of the war, partly because it was cheaper than a Panther and partly because it broke down less often. By the end of 1944, German armored formations on the Eastern Front were a mixture of perhaps one Panther for every 3 or 4 other vehicles, simply because the Panthers could not be kept running in numbers. The Soviet side knew. Soviet armor commanders who had captured hundreds of intact or near-intact Panthers during the long advance from Kursk to the Vistula examined the tanks carefully. They reverse-engineered the gun, the optics, the armor. They tested the engines on Soviet test stands. They drove the captured tanks around training grounds and recorded what broke. And they concluded, in a series of post-war studies that have since been declassified, that the Panther's final drive was a manufactured weakness, a structural flaw that the Germans could not fix and that the Red Army could exploit. The Soviet operational doctrine of the late war, the so-called deep battle concept, was built around the assumption that German armor could be forced to move repeatedly between threatened sectors. Every move cost the Germans tanks. The Soviets did not have to outfight the Panthers tank for tank. They had to force the Panthers to drive. The driving did the rest. The contrast with American practice deserves to be drawn out. The Sherman, the workhorse of the Western Allied armored forces, was a less impressive tank than the Panther in almost every individual technical category.
Its gun was less powerful, its armor was thinner and not as well sloped, its sights were not as good, its silhouette was higher. By the standards of a one-on-one engagement, the Sherman was inferior. But the Sherman's final drive used double helical herringbone gears machined from properly heat-treated alloy steel in American factories that had no shortage of nickel, molybdenum, or tungsten. American Shermans completed road marches of hundreds of kilometers without losing tanks to mechanical failure. They went into the Battle of the Bulge with operational readiness rates above 80%. They came out with the same. The Sherman drivetrain was rugged. The Sherman's final drive housing was forged steel, not cast, with internal gear geometry that distributed loads across multiple teeth simultaneously. The same factories that produced the Sherman's final drives produced final drives for the M10 tank destroyer, the M4 105mm assault gun, and the M32 recovery vehicle. And they produced them by the tens of thousands, using the same machine tools, the same metallurgical specifications, the same heat treatment cycles. American production engineering had solved the problem that Germans could not solve. Not because American engineers were more brilliant, because American factories had the time, the materials, and the production discipline that German factories, by 1943, no longer had. There is a temptation to read this story as a triumphalist American narrative, the kind of thing that gets written into popular histories about how the arsenal of democracy outproduced and out-engineered the Reich. That reading is incomplete. The Panther's final drive was not bad because German engineers were incompetent. It was bad because German engineers were forced to design within constraints that no engineering team should have been asked to accept. The original planetary final drive specification was sound. The case-hardened high-alloy steel that had been specified for the gears was sound. The detailed mechanical layout was sound. What was unsound was the wartime situation in which those original specifications could not be maintained, in which planetary gears could not be cut in sufficient quantity, in which high-alloy steel was not available in sufficient supply, in which case-hardening cycles could not be run for the full required duration. The Panther's final drive failed because the Reich could no longer manufacture what its own engineers had designed. This is the deeper lesson, the one that does not show up in the photographs of Soviet soldiers standing on knocked-out Panthers, or in the post-war interviews with German tank commanders, or in the technical drawings reprinted in tank enthusiast books. The mechanical failure was a symptom. The underlying disease was an industrial economy that had been mobilized for short, decisive wars and was now grinding into the fourth and fifth years of a sustained attritional conflict that it could no longer support. Germany was running out of strategic alloys, running out of machine tool capacity, running out of skilled labor, running out of the time it took to do things properly. Carl Otto Sauer's brutal simplifications, his demands to substitute easier-to-manufacture parts for the original engineering specifications, were not the personal failures of one Nazi administrator. They were the response of an industrial system that had no other choice. The simplifications increased production. They reduced reliability. They put more Panthers on the production line and more broken Panthers on the side of the road. By 1944, the ratio of new Panthers being delivered to existing Panthers being lost to mechanical failure was approximately balanced. Germany was running an enormously expensive industrial program to maintain a fleet of tanks that could not be kept operational. The Eastern Front campaigns of 1944 and 1945, the great Soviet operations that pushed the German army back from Belarus to East Prussia to Berlin, were not won because the Red Army's tanks were technically superior to the German tanks. Tank for tank, the Panther was usually better than the T-34-85 that opposed it. They were won because the Soviet tanks were operational and the German tanks, half the time, were not. They were won because Soviet T-34s could complete the long road marches that the offensive operations required and Panthers could not. They were won because Soviet drivetrain engineering, less sophisticated than German drivetrain engineering on paper, was actually less sophisticated than German drivetrain engineering by design. The T-34's transmission was crude,
The steering was tiring, the controls heavy, but the gears were generously sized, the steel was adequate, and the whole system was forgiving of the kind of abuse that mass-produced military equipment inevitably receives. The Soviet engineering philosophy assumed that operators would be inexperienced, that maintenance would be inadequate, that materials would be marginal, and designed accordingly. The German engineering philosophy assumed that operators would be skilled, maintenance would be diligent, and materials would be premium, and built that way. By 1944, neither assumption was true on the German side. The premium materials were gone. The diligent maintenance was impossible. The skilled operators were dead, and the tanks broke down. The most damning illustration of this, the moment that captures the entire dynamic, is a statistic from the highest point of Panther deployment on the Eastern Front. In September of 1944, Wehrmacht records show 728 Panthers on the strength of armored units in the East. Of those 728, 522 were listed as operational. That was the high watermark. That was the best ratio Germany ever achieved on the Eastern Front, after 18 months of attempted improvements to the final drive, the engine, the transmission, the fuel pumps, and every other mechanical system that had been failing since Kursk. 522 operational out of 728 on hand. 72%. That was the peak. Most of the time, it was worse. By comparison, the Red Army's tank armies operating in the same theater at the same time routinely achieved operational rates between 85 and 95%. Soviet T-34-85s and IS-2 heavy tanks, products of factories in the Urals that worked in temperatures below freezing for half the year and that were staffed largely by women and adolescents, were available for combat at significantly higher rates than the products of MAN and Daimler-Benz in temperate Germany. That is the gap. That is the entire war on the Eastern Front in one number. Not the gap in tank design quality, where Germany had an edge. Not the gap in tactical skill, where individual panzer crews were often better trained than their Soviet counterparts. The gap in operational readiness. The gap between how many tanks each side could put on the road every morning, ready to fight.
The Panther survived the war, of course. Several hundred examples were captured intact by the Allies. The Red Army used a number of them in the immediate post-war years until spare parts ran out. The French Army operated Panthers in the late 1940s for similar reasons. By the early 1950s, all of them had been scrapped or moved to museums, replaced by post-war designs that had learned the right lessons. The British Centurion, which began design during the war and entered service in 1946, had a properly engineered drivetrain with helical gears in correctly hardened alloy steel. The American M26 Pershing, which had reached Europe in tiny numbers in early 1945, similarly used American production-grade gears that did not fail. The Soviet IS-3 and the post-war T-54 inherited the T-34's philosophy of robustness over refinement. The Panther's failures left no permanent technical legacy. No post-war tank designer ever again specified straight-cut spur gears for the final drive of a 45-ton armored vehicle. The lesson, paid for in burned-out tanks abandoned beside Ukrainian roads, was thoroughly absorbed. But the strategic lesson, the deeper one, was not always absorbed. The Panther's story is sometimes still told as if it were a story of a beautiful piece of engineering tragically undone by the petty politics of Karl Otto Sauer, or by Hitler's interference in technical matters, or by the rush to deploy the tank at Kursk before it was ready. These explanations are not wrong, but they miss the point. The Panther's final drive was a symptom of an industrial system that could no longer support what its engineers wanted to build. The decision to simplify the gears was not made by a designer. It was made by a country that no longer had the steel.
In a museum in Münster, in northern Germany, there is a restored Panther Ausf G with its right-side final drive housing cut away for display. The visitor can see inside the housing the two stages of spur gears, the large drive gear engaging with the smaller pinion, the bearings on the input and output shafts, the splined connection to the drive sprocket. The gear teeth are still there, still meshed, still showing the geometry that defined the architecture of failure.
The teeth are clean and sharp because this particular tank has been mechanically restored and never driven hard. But the geometry is the same as the geometry that put 44 Panthers into the workshop pool at Kursk after the third day of fighting. The geometry that left 30 Panthers abandoned along the roads of Normandy in August of 1944. The geometry that allowed 522 out of 728 Panthers to be operational on the best single day of the Eastern Front's worst year for the German army. The geometry that, more than any other single piece of metal in the entire war, decided how the German army would lose. In a war fought between industries, the tank that could not turn a corner without breaking its gears was the tank that lost the war. Not because the men inside it were not brave, and not because the engineers who designed it were not skilled, but because the country that built it could no longer afford to build it properly. The Panther's final drive is not a famous failure. It does not appear in the popular memory of the war alongside the Tiger's reputation or the T-34's legend or the Sherman's reliability. It sits quietly in the housing where the drive shaft meets the sprocket, on every Panther preserved in every museum in the world. 600 pounds of cast steel and machined gear teeth, the most consequential mechanical failure of the entire Eastern Front, hiding in plain sight where almost nobody looks for it. The men who drove the Panthers knew. The Soviet generals who fought them knew. The British technical intelligence officers who examined them after capture knew. And the historians who later read the reports and counted the abandoned tanks and traced the operational readiness rates back to their underlying causes knew. The rest of us who watch the documentaries and read the popular histories and stand in front of the restored Panthers in the museums mostly do not know. We see the gun, the armor, the sloped front plate, the long, graceful line of the hull. We do not see the gears. The gears are inside, in the dark, where the failure happened. But the gears are the story. The war was decided by them, and by the country that could no longer make them right. The Panther was a beautiful tank. It was also the most expensive piece of machinery Germany ever built that could not be relied on to drive 75 kilometers without braking. That is the contradiction at the heart of the entire German war effort on the Eastern Front, and the final drive is where the contradiction lived. Quiet, hidden, never famous, never on the cover of any book. It was enough to lose a war with. In a war decided by what worked, it was more than enough.